Here we are again. Nuggets are up. I think it's 25-17. I don't know the series right now, but Nuggets need to win. This is your worksheet 11. Let's see. For each of the following series, use an appropriate comparison test. Indicate all the stuff. Okay, so I'm going to use, I typically just default to the limit comparison test because I don't want to decide between a B sub k and A sub k sequence, which is bigger. So for B sub k, your choice, focus on your leading terms. 3 over 2 to the k, that could work, or 1 over 2 to the k, that could work. Let's use 1 over 2 to the k. The test, limit comparison test. Okay, so limit comparison test, we got to do a couple things. We need to look at our B sub k as a series. So take the B sub k sequence, look at it as a series, and decide if it converges or not. This converges, this series, the comparing series, converges as geometric series test, geometric series test. The size of the ratio is a half, and that's less than 1. All right, then we have an original series, we have a comparing series, and for the limit comparison test to imply convergence for this one. So the original can only do what your comparing does. If your comparing converges, your original can only converge. If your comparing diverges, the best you can say is that your original diverges. Otherwise, inconclusive. So converging comparing series with the limit comparison, you want to take this limit, and it needs to not be infinity to be able to conclude convergence also for the original. So take your limit, k getting big. Isn't it? Oh, what is it? I forget. Is it a sub k over b sub k? Is it absolute value? There we go. Over here on the left, a sub k over b sub k for your limit comparison. No absolute value bars. A sub k divided by b sub k is the reciprocal there. You know what? I'm going to go back. It doesn't matter. So you could change this to a 3 and make this a 3, and then they cancel, but it's fine. So, all right. So what do we end up with? We have limit 3 times 2 to the k. That's not 6 to the k. 2 to the k plus 4. The limit right now is infinite over infinite. Maybe divide out by 2 to the k. And that's 3. The numerator, this would be 3. Denominator would be 1 plus 4 over 2 to the k. This 2 to the k over 2 to the k is 1. 4 over 2 to the k is 4 over 2 to the k. This piece goes to 0, and you get 3. So yeah, that's not infinite. So a couple things. We have comparing sequence, comparing series that converges. Our limit wasn't infinite, so our original series converges. This one, let's focus on the original terms. That's k over k to the 3 halves. K over k to the 3 halves is 1 over k to the half. The series, 1 over k to the half, p series test. P is a half, that's less than 1, that series diverges when we take our limit. We hope to imply that our original diverges just like our comparing does, but that will only happen now when the limit is not 0. AK, k cubed plus 8k over b sub k, so k to the half over 1. This is k to the 3 halves over root k cubed plus 8k. So a couple things. With this whole root in the denominator, either you need to do some good algebra where you factor out k cubed, and I'll show you that. Or you just you focus on the leading terms and you say that this limit is about the same as k to the 3 halves over root of k cubed, where you forget the whole 8k. And then this is 1. And that was not 0. So that series original diverges. If you were going to factor, then this is how that works. You have k to the 3 halves in the numerator. We have a limit. In your denominator, factor out a k cubed. So in the denominator, you can't distribute the root to the k cubed in the 8k because of the plus. So if it were multiplied, then you could distribute the root to each factor. That's why we're going to factor. So k cubed, that gives us a 1 plus 8k over k cubed. That's limit k big, k cubed over 3. So k to the 3 halves over, okay, now we have a factorization. We have k cubed and we have this stuff. We can distribute the root to each piece. So that's the root of k cubed times the root of 1 plus 8k over k cubed is 8 over k squared. All right, now take your limit. This piece, whoops, this piece goes to 0. So then we got root 1 plus 0. That's just root 1. These cancel, and you get back to 1. 1. Just like we had here. Okay, consider the series. That's alternating. Show the series can alternating series, 2 conditions. Okay, so your series looks like this. This here, this is your a sub k for the alternating series test. So first thing you should do is decide that 1 over k to the 3 halves limits or converges to 0, and it does. Check. 2, show that it needs to be positive. And that may not be one of the two that we're talking about. And then the other is that it decreases, and it does. Check, because you have a fixed number over a denominator that's getting bigger. If you gave a reason, you'd say like number over denominator increasing. So these 3 things together tell you that the series converges. Determine how many terms of the series must be summed, and to be sure that the absolute error or the size of the error, or the positive version of the error is less than a tenth. So the easiest way to do this is to list out your terms and find one that's less than a tenth, and then you take the previous many terms. So if our series was negative 1 to the k plus 1, 1 over k to the 3 halves, and you listed out terms. And I'll list the negative and positives here because that'll matter when we take the sum, but not for the error. Okay, plug in a 1. First term's positive, negative 1 to the 2 times 1 over 1 plus negative 1 to the 2 plus 1, 1 over 2 to the 3 halves, plus negative 1 to the 3 plus 1 times 1 over 3 to the 3 halves. And then let's just see where we're at. So this is 1, the first term, minus 1 over root 8 minus, no, plus 1 over root 27. Then we'd have minus 1 over 4 to the 3 halves. That's going to be 2 cubed. That's going to be, is that right? Yeah, 8. And we're looking for a term that's less than a tenth. So we need to keep going. So plus 1 over the 5th term. Here we need more space. Fifth term plus 5 to the 3 halves. That's the root of 125. The root of 125 is, what's the root of 125? 25 times 5, 5 root 5. And that one is smaller than a tenth, because root 5, if this were, let's see, if this were 10, that would mean 5 root 4, that's 5 times 2, that's 10, but it's 5 root 5. So 5 root 5 is bigger than 10. That means 1 over 5 root 5 is less than 1/10. Okay, so you found a term. It's this term that's less than a tenth. So if you want to determine how many terms of the series you got to add up so that the error between the estimate and the actual sum is less than a tenth, then you add up the previous 4 terms. That's the thing with alternating series. If you add up one term, the error between one term and the actual sum, whatever this adds up to, the error is less than 1 over root 8. If you add up 2 terms, the error is less than 1 over root 27. Add up 3 terms, the error is less than an eighth. Add up 4 terms, the error is less than 1 over 5 root 5, and that's less than a tenth, so we're within a tenth. So we need 4 terms. Estimate the value of the series with an absolute error less than a tenth round to the, so this is where you add up the 4 terms. So the partial sum of 4 terms is 1 minus that plus 1 over root 27 minus an eighth. I'm not going to use a calculator and round. If this were the exam, then without a calculator, this is what you leave your answer as. Are we done? No, we're not done. Oh, ratio test. Mercy. Let's see. Ratio test. Limit k to big. A sub k plus 1 is 3 over k plus 1 times 2 to k plus 1 times reciprocal of kth term. And we end up with the, okay, so 3's cancel. We have k and 2 to the k. We have k plus 1. 2 to the k plus 1 is 2 to the k times 2. 2 to the k's cancel. And we have a half limit k to big, k over k plus 1. You don't need the bars anymore because this is positive anyways. And that's 1. So we end up with a half times 1, and that's less than 1. So our R for the ratio test is our limit, and that's 1/2. It's less than 1, so our series converges. Ratio test here, k to big, absolute value, -1 to the k plus 1. That's the k plus 1th term multiplied by the reciprocal of the kth term. Okie doke. All of your negative things go away because they're reduced to positive ones with the bars. and everything's positive at this point. So we don't need the bars anymore. Here's our fraction. The k factorial k plus 1 leaves us with a k plus 1 in the denominator. Oh, you know what? The k plus 1th term. You know, I did that a little wrong. Let's see. Let's go back. This should be k plus 1th over kth term. So this should be k plus 2. Yeah. All right. So k plus 1, k plus 2. And this, oh, here, let's do this. Okay. So these two. K factorial k plus 1 factorial gives us a k plus 1. These are gone. We have k plus 2 to the 100, k plus 1 to the 100. So k plus 1 and k plus 2, all that to, well, this is to the 100, this is to the 100. K plus 1 to the 101. When you're multiplying exponential expressions with the same base, k plus 1, you're going to add up the exponents to get 101. Then the degree of the denominator is higher, denominator wins, we go to 0. So the limit is 0 and we converge. And then the last one. So you know, okay, so ratio test, anytime you have a mix of like geometric and geometric there, 2 to the k, and p series there, you're doing the ratio test. Factorials, ratio test, factorials, ratio test. So limit k to big, k plus 1 squared, 3 times k plus 1 factorial over k plus 1 factorial times reciprocal. All right. Okay. So let's think for a minute. K squared, k plus 1 squared, that's going to limit to 1 because the degree of the denominator is 2, degree of the numerator is 2 when you FOIL that out, and the leading coefficients is 1 and 1. So forget those for a minute. Those will limit to 1. The rest of them, we have k factorial, k plus 1. That'll give us a k plus 1. Then, you know what? Maybe I shouldn't have forgotten the k squared. Let's put that back in. And then k plus 1. Okay, the 3k plus 1, that's 3k plus 3 factorial. And then with the 3k, that'll leave us with 3 extra terms in the numerator. 3k plus 3, 3k plus 2, 3k plus 1. All right. The degree in the numerator has got to be bigger. Degree in the denominator is 3. When you FOIL, here we have k squared, and then 1, 2, 3. That's going to be k to the 5. So degree in the numerator is bigger, and we get infinite. Diverges infinite. Okay, degree numerator is 5. Degree denominator is 2. Degree numerator bigger than degree denominator, that gives us infinite. Okie doke. Y'all take care. Have a good rest of your evening or your day or whatever what's going on.